Next we have Patrick Farrell from Cray. Something I want to say about Patrick is that he has been really tireless in his efforts on the pack to make a difference, and we really appreciate your contributions. We had some sort of sparse involvement at one point, and when Patrick showed up, we got a lot more comments and a lot more push, so thanks. Patrick is a Lustre developer and a kernel programming enthusiast, working for Cray Incorporated. For better or for worse, Lustre has been his first experience with a large software system. You're doing great. Ladies and gentlemen, Patrick Farrell.
Thank you.
Rock on, pal.
Good morning. Let's figure out our slide advancer. Okay, that works how it should. Good morning, everyone. I'm here to talk about shared file performance in Lustre and some work Cray is doing to improve it. For those of you who are at the Developers Day in Livermore, a lot of this will look very familiar. Sorry. Okay, there we go. So, when you're writing out your data in HPC, generally speaking, you use one of two approaches. You write it all out to a single shared file, which all of the nodes in your job will write to, or you create a file for every process. With Lustre, file per process scales great. Shared file doesn't. But there are still some issues with file per process, so we can't just say to users, just do file per process. Some sites do, but some users complain anyway. The fundamental issues with it are a heavy metadata load for large jobs. If you've got 1 million cores, that's 1 million processes. That's 1 million files. That's a lot of metadata load, both during the job, so for job startup, and then after the job, because eventually you probably want to collate the data into a single file and chew on it. So ideally, it would be better if you could do all of your work in a single file. That'd be nice. Whoop. Okay, there we go. Sorry. So, talking about shared file I/O, the most common way HPC applications do shared file I/O is they use the MPI/IO library with the collective buffering option on it. And that does what's called I/O aggregation or collective buffering. So all of the nodes in the process will ship their data across the network to a small number of aggregators, which are sort of nominated to be the ones that interact with the file system. So you have 100,000 nodes in your job, but maybe 50 aggregators, and the aggregators are the only ones which actually write to the Lustre file system. And so that's the case we're looking at optimizing here. So when you're using that library will get you strided, non-overlapping writes. So what that means is a particular client is responsible for particular blocks, and if, in the example here, you have 2 clients, the first client would be responsible for block 0, block 2, and block 4, going on, and client 2 would be responsible for block 1 and block 3. The idea being that they work in strides, so they do not ever try to write to the same blocks of the file system. And so currently, the MPI/IO collective buffering, which is specifically for Lustre, that is set up so there's one client per OST. And this is in the upstream MPI/IO, that's the Lustre 80IO. It's all freely available. I think, I want to say Argonne was involved in getting it together, and some of the people from CFS back in those days. So the reason for they do one client per OST is because that's when the bandwidth is best. And going from 1 to 2 clients per OST actually reduces the bandwidth dramatically when both clients are writing to the same file. And adding more clients after 2 doesn't really help. It's a huge problem because in real systems, an individual OST can handle the full bandwidth from several clients, and you can hit that limit with file per process. So as an example, the latest Seagate systems, the one that Cray calls the Synexion 2000, they've got enough bandwidth that if you're doing file per process, you can point 8 clients at them, and that's about when they top out. But if you're doing single shared file, you only get 1 client per OST, so you get 1/8 of the maximum bandwidth of the file system. It's not the most fun. You can see that actually documented on the LANL poster about their upcoming system. So here we've got a little graph. This is unfortunately not from a brand new fancy big system like the Synexion 2000. It's from something a little older around Cray. But you can see the top line is file per process or independent writing. And we go 1 client, 2 client, the bandwidth nearly doubles. Unfortunately, this OST tops out at about 2 clients. But then we can compare that to the green line, which is shared file, and you go from one client all the way on the left to two clients. Bandwidth drops by roughly 50%. And as you keep adding clients up to about 8, you finally get back to about where you started. If this graph went further to 16 or 32, you'd see it drop off again. You never really get any faster than the bandwidth you get with a single client when doing single shared file. I'll cover what the blue line is in a minute. So, why doesn't shared file I/O scale in Lustre? Like we talked about, in the shared file I/O being done by the MPI IO library, the writes are strided, they don't overlap. So since they don't overlap, you should be able to have the clients writing in parallel. Clearly that's not the case. So why can't the two clients write in parallel? And the answer is that because of the LDLM, which is those are Lustre's distributed locks, the ones that are passed around between clients and servers to manage contention between clients, because of the design of LDLM, the writes are serialized, and more than two clients are slower than one. And remember that these two clients aren't actually trying to write to the same block of data, so the lock contention is a design artifact rather than something fundamental. So now we're gonna explain why. So this is a single OST view of a file, which you can also scale up to think of as the view of an individual OST in a striped file. We're going to talk about two clients doing strided writes. So client 1 asks to write segment 0. So this is what the server does when it gets that request. It says there are no locks on the file. It says, oh, hey, I bet I know what you're going to do. You're going to come back and want to write another part of the file later. So the server expands the lock, and because there are no other locks on this file at this time, it grants a lock on the whole file. Client 2 shows up and says, hi, I'd like to write segment 1. This conflicts with the expanded lock granted to client 1. So the server has to request that lock back. So client 1 has to rush to get its data down and give the lock back to the server. Now, the server will process the lock request from client 2. And guess what? There are no locks on that file because the client 1 lock was just canceled. The client 2 lock is expanded from the start of segment 1 to the end of the file. You can probably see where this is going. Client 1 comes back, says I want to write segment 2. That conflicts with the expanded lock granted to client 2. The lock is called back. And so essentially what happens is the two clients spend the entire I/O exchanging locks without ever trying to write to the same region of the file. So it's not quite as bad as it sounds explaining that. It's actually even worse than being serialized so that's why it's worse than one client, because you spend the extra time getting and exchanging the lock. So you have to go back and forth to the server to hand a lock back and forth. It's even slower than if one client can just get a lock and do the writing. Now, it's a little better than it looks like from up there, because in practice, client 1 will usually we measured it 2 to 4 blocks written at a 1 meg block size before it hands the lock back. It's still pretty bad though, because you're only getting about 4 blocks down, and then you have to hand the lock back, and you should both clients should be able to write in parallel. So the first thought is, what about not expanding locks? That would avoid this contention we're talking about. The clients can write in parallel. We tried that. It was worse. The reason for that is that when you're in that mode, you need to get a lock for every single write. So instead of the process for a write being go to server, get lock, then write, the process for every single write is go to server, get lock, go to server with write data. So you have an extra round trip for every single write. And what we found was that that's actually slower than simply doing the lock exchange, because that increased latency. So that was the blue line at the very bottom of the graph where performance was bad and stayed bad all across. So a proposal for dealing with this is something called Lockahead. This is a way to allow clients to request locks on file regions in advance of I/O. It's an ioctal. You would basically specify, I want a lock from the start of a particular byte range to the end of a particular byte range, and then it makes that lock request to the server. But it's done asynchronously, so you can make 1,000 of them very quickly, and the server will return the lock. So you can do that, for example, in advance of your I/O. So the pluses of this, it's very flexible. it's not limited to optimizing strided I/O, since you can request a lock in advance of need. You could request locks for a different I/O pattern if you had one. And then it's also not too bad to implement. There's some existing machinery that's useful. Some problems with it: a very large file written in this manner can wind up with, for example, if you're locking every meg and you write a few terabytes, you'll end up with millions and millions of locks. That does have some negative implications. And writing this, I say it's easy to implement. There's some bugs that have come up, not all of which are directly in this code. So to explain it a little better, do some graphics. So imagine requesting the lock ahead of time. Client 1 wants to write segment 0. But before it starts the write process, it requests locks on the segments it plans to do I/O on. So in this case, 0, 2, 4, 6, 8. The server grants those locks, which are not expanded. That's just part of the feature of it. You request on a specific extent, and it's granted only on that extent. And then client 2, and then client 1 can start writing at this point, and client 2 separately requests locks on the extents it wants to write on, and then they simply begin to write. And then both clients are able to write and do I/O in parallel. No conflicting locks, no handing the lock back and forth. So real quick, as a digression, Lustre does have an existing mechanism for improving this sort of shared file I/O, for avoiding contention in a shared file. That's something called group locks. And essentially, with a group lock, your different clients can all sign up to turn off LDLM locking on a file. They join a group lock, and a whole bunch of clients can hold the same lock totally exclusively on the same file. The problem with that is you have, more than one client holds the lock. So you have two clients, and we wind up with what was called write visibility issues. For example, client 1 writes a segment of the file. Client 2, if it already has that segment of the file in cache, client 2 doesn't realize client 1 has modified anything because there's a lock on that area of the file. So it's very problematic. You actually have to release the group lock to get write visibility between the clients. And releasing the group lock means you've got to write out all the data, that sort of thing. So for some things, that's not a problem because all you do is write, and you never look at anyone else's data, and that's fine. However, HDF5 and some of the other containerized formats have in-file metadata, and that means by default, the way they're written, they need to be able to see other clients' writes in the middle of the job. And so as a result, the write visibility issues of group locks are a bit of a non-starter. You can fsync and release your group lock after every time you write, but the problem is you do a great number of writes, and if you're fsyncing and getting the new lock every time, the speed benefits go away. So talking a little bit about the performance we're hoping to get, we do have some early results, but I unfortunately don't have a pretty graph for you. So the early results showed that at least for small to medium-sized files up to a few hundred gigs, we were seeing equal to file per process performance, so we were able to fully drive the OST. Unfortunately, much past that, we started to lock up, and that's something I'm still working on, going to be talking about at the Developers Day. So like I said, this feature is intended to match up with the MPIO collective buffering. That's a freely available feature in the Lustre ADIO. That's part of the MPIO library. And you can see that's how you run it with IOR. You specify MPIO and C for collective buffering. Cray is going to make an ADIO patch available once this is advanced enough that it's ready. And you will need to relink your codes against the new library, but any code that was already set up to do collective I/O through MPIO does not need to change to take advantage of this. So just a little bit about the implementation, sort of a teaser for the Developers Day talk. We're reusing a lot of the asynchronous glimpse lock implementation because normally Lustre's lock requests are synchronous and asynchronous requests require some different machinery. Some of that already exists. We're also adding an LDLM flag that tells the server not to expand the lock, so the server side can recognize this is a special request. Don't try to optimize the lock size. The client knows what it wanted. And they're going to go into great detail at the Developers Day tomorrow. This is targeted as a feature for 2.8. We'll see. It's targeted. It's basically sort of, you might call code complete, but there are bugs at this point, and we'll see what it takes to resolve those. Unfortunately, this is client and server-side changes, so you're not going to be able to take, for example, your 2.8 clients and use this on your 2.5 servers. You're going to need new clients, new servers. So harking back to the Developers Day at Livermore, I proposed something called strided locks, and I'm not going to go into detail here. That was an earlier idea for dealing with this. There's still an incomplete prototype up at Intel's Jira at LU6148. It looks like Lockahead locks are going to meet our needs, and they're a lot easier to deal with, easier to code for. They'll make Lustre less complex for future use. On the other hand, if it turns out that Lockahead locks dive off a cliff above a certain file size, we may resurrect strided locks. So if anyone's interested, you can ask me about that. Finally, just a quick thank you to the guys at Cray who got me started, which is David Kanak and Bob Cernahouse. And thanks especially to Jin-Sun Shung, who is not here, and Andreas Dilger, who is, for the suggestion of Lockahead as a simpler solution than strided locking, and assistance with design and bug fix along the way. And I also like to give a shout out to Oleg Drokin, who gave me a hint on how to solve the bug I'm fighting with currently on Monday. So, and that's the Lockahead works up in LU6179. When the ADIO patch is ready, which we're going to optimize it a bit once we've got the code that fully works, and then we'll make it available. But we'll put a link there, and we'll also try to submit that to the upstream. I'm not actually sure who's responsible for MPIOs upstream, but people at Cray who work with it say they're in touch with those folks. So the way I explained this to somebody was this talk is, hey, we have this delicious sausage, you might like to eat it. Tomorrow I'm going to get out the grinder and some pigs and explain how the sausage is made. So any questions?